right. So you've got these two canoes touching at rest on a lake. The occupants push away from each other, and they have these speeds. So what type of collision is this? What type of collision would you categorize this as? It is an explosion, yeah. Because they start off as one object and then become many, or more than one. So yes, this is an explosion. And that's exactly where I would start my Y. So let me just adjust my font size here. So that's where I start. This is an explosion. So momentum is conserved and K increases in the system. See what else they have to do. Yeah, okay. One of the parts here of my rubric is that impulses are shown and corrected in diagram or mentioned. So I could draw those in my diagram, and I think that's what I'll do rather than mention. All right. So I'm going to make sure I include the impulses, maybe in the before diagram. That's kind of when they happen. All right. So let's see how well I can draw canoes. So here we go. Oops. Canoe number 1, canoe number 2. Do they call them A or B or anything? No, 1 and 2. Okay. And they have they're not moving, so their initial momentums are 0. I'm going to make a note of that. Momentum 1 equals momentum 2, which equals 0. So that, like, if I was grading this and I didn't see any momentums mentioned, I would say, did they just forget about them? Or did they realize that they were 0? And by kind of writing it in there, it cements it to the person reading it, saying, hey, they knew about them. They didn't forget about them, so give them full credit. Now I'm going to put my impulses in, and I know that all impulses come in pairs, because that's how the universe works, and that's why forces come in pairs. So whatever impulse there is on canoe 1, there's an equal and opposite impulse on canoe 2. So there's an impulse in this direction, and I'm actually going to draw that right on my canoe. It's an impulse on canoe 2 by canoe 1 in that direction, and there's the exact same one on canoe 1 by canoe 2 over here. So equal but opposite impulses, each one acts on the opposite body. Then, let's see. Afterwards, canoe 1, canoe 2. I went to the Max School of Drawing on his phone, so he's doesn't know I'm talking to him. Okay. Hey, Max. I was referring to you. This is the momentum of 2 afterwards. We'll call it 2A. And this is the momentum of 1 afterwards. Let's see. Clear links and understand physics of the problem. Yep. Clear links to the problems get through them extra high. All momentum shown incorrect. Yep. Impulse is shown incorrect. Yeah. I said I went to the Max School of Drawing. But yours are better.
Well, I'm
All right.
Mr. Gardner, can you just go back up just one more time?
That far enough? You want to? Yes, Mr. Julian.
So that's a J, right?
Yep.
The J is
Impulse.
The impulse isn't the same as meters per second. So
No, that would be a velocity.
yeah. So how did you calculate the joules?
There are no joules. Joules would be J if it was a unit. This is J as a variable.
I thought that was 12 and 21.
No, that's saying the impulse on canoe 2 caused by canoe 1,
Okay.
and the impulse on canoe 1 caused by canoe 2. Matt, you good?
Yeah. Thank you.
Okay. All right. Get a little warm. All right, so I need to start with valid equations. So, grab my equation sheet. Let's see where there it is. And I'm dealing with momentum here, so it'd be good to have momentum. All right. So that's the only equation I need for my equation sheet. But we start with exactly from the diagram. And we have momentum of 1 plus the momentum of 2 equals momentum of 1 after plus the momentum of 2 after. That's the idea of my conservation of momentum. There's some squiggle for an equal sign there in the middle. Which direction do you guys want to call positive? These to the right?
Yeah.
Okay, so we'll call anything that moves to the right positive. Because with vectors, that's important. Let's see, the momentum of number 1 to start with 0. The momentum of 2 to start with 0. Afterwards, we'd have the mass of 1, velocity of 1 after, plus the mass of 2, velocity of 2 after. And then I can start inputting the values that it told me canoe 1 has a speed of 0.59 meters per second. And I'm going to assume that in my drawing I put that way, and 290 kilograms. So 290 kilograms, nice units for me. 0.59, I think it was. It's decided its last block is going to mess with me. So then plus M2, which we don't know. And, this should be negative, shouldn't it? And 0.38 meters per second. And do I expect an answer larger or smaller than 290? Larger, yeah. because those two are going to have to be the same amount, and 0.38 is less than 0.59, so I expect an answer bigger than 290. So if I get one less than 290, I check my count.
Did they give us the mass, the first one on the...
Yep.
Okay.
Yeah, it's in the, alright. On to number 2. Number 2 is, what type of collision?
Is that an explosion?
It's an explosion again. Yep. So, very, very similar to what we just did. Only difference is we're changing up what the objects are. In this one, rather than 2 canoes, we've got a hockey player and his helmet that he talks is directly in front of him. Now, why would they pick something like a hockey player? Why not a football player?
He's on ice.
Because he's on ice, which makes him and the helmet an isolated system, which makes life easier. All right. If he wasn't, if it was like a football player standing with cleats, he would a little bit though, because but him and the Earth would move back, and that would be so minuscule it
wouldn't be like noticeable.
It wouldn't be noticeable or even measurable. So that's why they choose the isolated systems to make life easier and more friendly numbers. So let's see, we can type into this first. Again, 24. This is again an explosion. So momentum is conserved due to the impulses being equal but opposite on the player and the helmet. Because remember, I could either draw in the impulses or I could just talk about them. But this time I just talk about them. But I showed that I understand that impulses always come in pairs. They're always equal and opposite. Alright, so beforehand, let's see. Why is that black? I can't see the color. Momentum of helmet and player equals 0. Whoops. Definitely losing it if I do an arrow for a 0. And then afterwards, which direction does the hockey player move afterwards? Backwards. To the left. So that would be the momentum of the hockey. And then we have our helmet. And this would be the momentum of the... Oh, so this should be the player. I am losing it. This is momentum of the helmet. This is momentum of the player. And then the how is going to be like identical. So why don't I, rather than copying something, let me grab this. All right. And then the momentum of the hockey helmet and the hockey player before equals the momentum of the player plus the momentum of the helmet afterwards. This we said was 0. This would be mass of the player, velocity of the player, plus mass of the helmet, velocity of the helmet. Very important to remember that those are velocities, so you've got to get your directions right. Alright? If you don't, you'll get frustrated, or just get wrong answers again and again and again. And now you can just substitute in like we did last time. And you'll be left with one value you don't know. And that's always a happy day with math.